Albert Einstein's Special Theory of Relativity in Approximately 5 Minutes by Graham Arthur Mackenzie of Explaining Concepts. Albert Einstein's Special Theory of Relativity can be summed up in 2 basic points. Number 1, the laws of physics should look the same for everyone, regardless of the speed at which they are moving. And number 2, the most accurate way of translating distances and times between 2 observers moving at different constant speeds is the Lorentz transformation. The first point is called the principle of relativity, and was first stated mathematically by the great Italian physicist Galileo Galilei in his eponymous transformation, the Galilean Transformation. It is essentially the definition of a physical law, and has never been refuted experimentally. The second point indicates the best method for translating physical data between 2 observers such that they are mutually intelligible and the first point is respected, that is, transforming. For hundreds of years, the method that physicists used to do this was the Galilean transformation. This method was superseded by the Lorentzian one because it was found that the former could not account properly for the behavior of light. The way that this came about is as follows. In the year 1887, 2 men named Albert Michelson and Edward Morley performed an experiment intended to provide direct evidence for the existence of a hypothetical, invisible, odorless, tasteless, nearly frictionless, all-pervasive substance called ether, which was supposed to be the physical stuff through which light, which was known at the time to be a wave phenomenon, propagated. Under the Galilean transformation, since light traveled relative to the ether at a known speed of approximately 300,000 kilometers per second, measuring its speed in a bunch of different directions, from a bunch of different locations at a bunch of different times, to avoid the possibility of being at rest relative to the ether, should have provided a bunch of different results, which would have indicated the speed and direction of the Earth relative to the ether, which, in turn, would have constituted the desired direct evidence for the latter. This is exactly what Michelson and Morley did, but no matter how they oriented their perfectly well-tuned and sufficiently accurate instruments, they always got exactly the same speed for light. Initially, scientists were so wedded to the idea of the ether and convinced of the universal validity of the Galilean transformation that they attempted to explain away Michelson and Morley's null results theoretically. The most successful of these attempts was made by a man named Hendrik Lorentz, who hypothesized that perhaps the arms of the measuring instruments were shrinking in the direction of the Earth's motion through the ether. Lorentz's transformation is his mathematical description of this, his hypothetical contraction. It accounted perfectly for the null results of the Michelson-Morley experiment, as it was designed to do, but unfortunately had a fatal flaw that led to other, much deeper, and more intellectually troubling problems. Einstein did not invent the special theory of relativity to account for the results of the Michelson-Morley experiment, but the way in which it happens to do so helps show why it is so cool and revolutionary. The position Einstein's theory takes in regards to the experiment is to ask, forget about all this unproven ether stuff, what do we know for a fact? And the answer it provides is, we apparently know for an experimental fact that light has the same speed for all observers, regardless of their relative constant motion. In the light of this assertion, Einstein goes on to point out that although Lorentz was motivated by an incorrect physical hypothesis, the transformation equations he came up with are apparently accurate across a wider domain of applicability than Galileo's. Considering how dependable the Galilean transformation had been to physicists over the centuries, taking a position which interprets the results of the Michelson-Morley experiment as proof that light apparently does not behave according to its rules, but rather to those of the Lorentzian one, instead of as a failure to provide evidence for the existence of the intellectually appealing, probable, and widely accepted though unproven ether, was no small feat of imagination on Einstein's part. Even more impressive than this, however, was how he fearlessly accepted the logical, yet initially quite strange-seeming, scientific consequences of his interpretation. Some of the major ones are as follows. Suppose I am standing on the side of a road, and you drive past me at 100,000 kilometers per second. If at the instant you pass me, there is a flash of light directly over our heads, I will see it outpace you off into the distance at a speed of 200,000 kilometers per second, whereas you will judge it to be racing ahead of you at 300,000. This means we will both consider ourselves to be at the center of the light sphere that the flash creates as it expands outwards into space. The only way such a thing is possible is if we both register mutually differing measurements of space and time. From my perspective, you will shrink in the direction of your motion, and your actions will slow down, and the same will be true of me for you. Put another way, since the speed of light is the same for all observers, no matter their relative uniform motion, each observer's judgment of simultaneity, and thereby their measurements of spaces and times, will be relative. This is why it was realized after Einstein's innovation that describing an object's position in either only space or only time would no longer suffice to locate it accurately. If you and I disagree about whether or not two events are simultaneous, we're going to need to put the events on a grid with 4 dimensions, 3 for space and 1 for time, in order to locate them with mutually sufficient accuracy. Hence, the special theory forever joined the formerly theoretically independent dimensions of space and time into the 4-dimensional spacetime. Some other consequences that the uninitiated might find odd follow from translating between observers via the Lorentz transformation. For example, the speed of light apparently acts as a sort of speed limit for objects in our universe. If one plugs into the Lorentz equations a velocity for an object that is equal to or greater than that of the speed of light, the equations spit out distances and times for the object that are mathematically imaginary. Furthermore, velocities less than the speed of light don't just straightforwardly add up under the Lorentzian transformation as they do under the Galilean. Calculating the relative speed of as large a number of objects with such velocities as you like, each one faster than the last, you will get closer and closer to the speed of light without ever actually reaching it. Put another way, it has been observed that the mass of a particle increases with its velocity. However, the greater an object's mass, the more energy it takes to increase its velocity. At a certain given point, it would take an infinite amount of energy to increase the object's velocity to that of the speed of light. Only light particles, and other objects with rest masses of 0, can move at the speed of light, and they can never move slower than this. Another outcome of the special theory involves the so-called most famous equation of all time, E = mc squared. The upshot of this equation is that mass and energy are equivalent. Therefore, in the same way that two distinct events separated only by time for one observer can be perceived by another as being separated only by space, an object which for one observer displays only the qualities of mass can display for another only the qualities of energy. It should be stated that the fact that data regarding objects with speeds relatively close to that of light cannot be accurately manipulated with the Galilean transformation does not mean that Galileo was wrong and Lorentz right. In fact, the relativistic laws of motion, which are based on Lorentz's equations, reduce to the Newtonian ones, which are based on Galileo's, at low speeds. Thus, the Newtonian laws are a special case of the relativistic ones. Evolutions of this kind, where a particular theory holds seemingly unimpeachable sway for a long time, only to be shown later to be actually a special case of an even more general theory, are the happy norm in science. Einstein's special theory of relativity is on as solid a footing as any other serious, widely accepted contemporary scientific theory, though there is some evidence that it may itself be a special case of yet another, even more general theory, the discovery of which hopefully lies somewhere in our future. Who knows, but perhaps you'll be the one to discover it.